Good day everyone, I'm Leonel Valiente and today I'm gonna talk about some sample problems for Chapter 6, Combined Axial and Bending Stresses. These are the contents of this video. The first problem is a problem that has figure P-902 and the second problem is a problem that has figure 18.11. Problem number 1. The problem asks to compare the maximum stress in bent road 1.5 inch square, where the load P is 1.5 inches, off center as shown in the figure P-902, with a maximum stress if the rod were straight and the load applied axially. To solve this problem, we must first find the P, which is applied off center. So we're going to use this formula, which is sigma is equal to negative P over A, which is our axial stress, minus 6m over BD squared. Now this formula came from the flexural formula, which is FB over MS, where M is the bending moment and S is the section modulus. For a rectangle beam, the section modulus is BD squared over 6, and therefore the equation transforms into 6m over BD squared. Therefore, sigma is equal to minus P over 0.5 squared, which is 1/2 squared, minus 6 here, and our bending moment is 0.5p over 0.5 times 0.5 squared. So sigma is equal to negative 28p. The value negative 28p is the value for P applied off center. Next is, and we're going to use this formula, sigma is equal to negative P over A, which is equal to our axial stress, which is equal to negative P over 0.5 squared, which would be negative 4. This is because 0.5 squared is equal to 1 over 4. We have obtained the value for P at off center, which is equal to negative 28p. The value for our P applied axially, which is negative 4. Therefore, we have negative 28 over negative 4p, which is our P is equal to 7 over 1 or 7. Now you might wonder why I used the negative sign in the formula that was being used. It's because the fibers here in this problem is in compression. That's why we need to use a negative sign in solving the problem. Problem number 2. A 4.8 meters column is acted upon by an axial gravity loaded of W kilonewton per meter as shown in the figure. The column in section is a wide flange beam 12 by 58, a 36 steel, which is a mild carbon steel with lower end built in. Assume the effective length factor X is equal to 0.80 and the effective length factor Y is 2.1. The yield strength is 248 megapascal and the modulus of elasticity is equal to 200,000 and the C sub M is equal to 0.85. These are the properties of the wide flange beam 12 by 58. The cross-sectional area is equal to 11,032 millimeters squared. and the overall depth of the beam is 309.63, and the flange width is 254.36 millimeter. The flange thickness is 16.28 millimeter. The web thickness is equal to 9.12 millimeter. The section modulus X is equal to 1280 times 10 to the power of 3 cubic millimeter, and the section modulus at Y is equal to 351 times 10 to the power of 3 cubic millimeter, and the radius of gyration at X is equal to 131.11 millimeter, and the radius gyration at Y is 63.75 millimeter. The problem asks to compute the allowable axial stress, the required spacing of lateral bracing for maximum uniform lateral loading, and the maximum uniform lateral loading allowed using the calculated spacing of lateral bracing. Now let's compute for the allowable axial stress. We'll be using this formula KL/R, which is the limiting slenderness ratio, and we're going to substitute the value here at X. So we have effective length factor X is equal to 0.8. It is given in the problem, and the length of the column, which is 4.8 meters or 4,800 millimeters, over the radius of gyration X, which is also given in the problem, valued at 134.11. So we have our limiting slenderness ratio for X is equal to 28.63. It's the same process, but we're going to substitute the value here at Y. So we have the effective length factor Y is equal to 2.1 multiplied by the length of the column over the radius of gyration Y, which is 63.75. Therefore, we have 158.12. Now let's solve for the critical slenderness ratio in order for us to be able to know what formula we're gonna use in computing for the allowable axial strength. So we have critical slenderness ratio is equal to square root of 2 pi squared multiplied by the modulus of elasticity over the yield strength. We have square root of 2 pi squared multiplied by 200,000, which is the value for our modulus of elasticity, over the yield strength, which is equal to 248 megapascal. So we have 126.17. Since our slenderness ratio is greater than our critical slenderness ratio, therefore we have to use the formula for allowable axial strength, which is equal to 12 pi squared multiplied by the modulus of elasticity over 23 multiplied by the limiting slenderness ratio squared. Substituting the value, we have 12 pi squared multiplied by 200,000 over 23 multiplied by 158.12 squared. Therefore, we have 41.19 megapascal as our allowable axial stress. Now let's proceed to the second number. In this part, we're going to solve the spacing of lateral bracing for maximum uniform lateral loading. So we're going to use this formula, L sub C, or the clear distance between the edge of a hole and the edge of next hole, or edge of connected steel plate in the direction of the load, which is equal to 200 multiplied by the flange width over square root of the yield strength, which is equal to 200 multiplied by 254.36 over the square root of 248. These values are already given in a problem. So we have 3,200 millimeter, or we have to use the distance of 3.23 meter for our spacing of lateral bracing for maximum uniform lateral loading. Now let's proceed to number 3. So we need to find the maximum uniform lateral loading. So for this, we have to start by solving for the axial stress, which is equal to load over area, which is equal to 7,600. This is given in a problem in a figure wherein there's a load of 76 kN over the area, which is 11,032 mm squared, which is equal to 6.89. Now let's find the value for the computed axial stress over the allowable axial strength. The value for our axial stress is 6.89 and the value for our allowable axial strength is 41.80. So we have the value for our axial stress over the allowable axial strength is equal to 0.167, which is greater than 0.15. Now this equation here states that when the value of the axial stress over the allowable axial strength exceeds 0.15, the beam column is said to be under large compression. And according to section 508.2 of NSCP, the member must satisfy the following requirements, which is the axial stress over the allowable axial strength plus the reduction coefficient C sub m multiplied by the bending stress over 1 minus the axial stress over Euler's critical stress is less than or equal 1.0. So in continuation for this, or in relation to this, we must use the Euler critical stress, which is 12 pi squared multiplied by the modulus of elasticity over the factor of safety, which is 23 multiplied by the limiting slenderness ratio squared. Substituting the values, we have 12 pi squared multiplied by 200,000 over 23 multiplied by 158.12 squared. So we have 41.19 megapascal as our value for the Euler's critical stress. Since we're able to solve for the value of the Euler critical stress, let's proceed in finding for the bending stress. But before that, we must first use the width thickness ratio. So width thickness ratio is equal to the flange width over 2 times the flange thickness, which is 254.36 36 over 2 multiplied by 6.28, which is equal to 7.81. And here is 170 over the yield strength, which is equal to 248. So 170 over the square root of 248 is 10.8. Since the width thickness ratio is lesser than 10.8, we have to use the formula for the allowable bending stress and tension, which is equal to 0.66 multiplied by the yield strength. Substituting the value, we have 0.66 multiplied by 248, which is the yield strength, which is equal to 163.68 megapascal. Now we're able to find the bending stress, since we have already the value for each one except for the bending stress. So we have 6.8 over 41.19 plus 0.85 multiplied by the bending stress over 1 minus 6.89 minus 41.19 multiplied by 163.68 is equal to 1, which we have our bending stress is equal to 133.50 megapascal. Now that we have the value for our bending stress, we can now solve for the moment capacity. So this is the formula for moment capacity. So F sub B is equal to the bending moment over the section modulus X. So we have 133.50 is equal to the moment or the bending moment over 1280 times 10 to the power of. So our bending moment is equal to 170.88 times 10 to the power of 6 Newton millimeter. Or we have 170.88 kilonewton per meter. Now let's proceed in finding for the maximum bending moment, which is equal to WL squared over 8, which is equal to the 170.88 equals to W multiplied by the length of the column, which is 4.8 squared over 8, which we have 59.33 kilonewton per meter. This value is the maximum uniform lateral loading allowed using the calculated spacing of lateral brace. That would be all. Thank you.